Today's video is about thermodynamics. Thermo meaning heat, dynamics means motion. So up until this point, we've learned about dynamics, which is the motion of physical objects. Then we talked about fluid dynamics, is the motion of fluids. Now we're going to talk about the motion of heat. So we're going to talk about temperature, heat, and heat transfers. So introduction. So in mechanics, we deal with quantities such as mass, position, velocity, acceleration, energy, momentum. What happens to the energy of a ball when I drop it on a floor? Well, it goes into the heat energy because it won't bounce back up to its original height. And that is heat energy. So the question is, what is heat energy? That answer is a little bit longer. So thermodynamics deals with quantities that deal with heat. Questions like, why can you put your hand into a 400-degree oven and not instantly get burned, but if you touch a metal rack, you do? Even though the air and the rack are actually at the same temperature, they have different energies content. So the construction of the temperature scale. So before we can talk about heat, we have to talk about temperature. So in order to do that, we have to choose a fixed temperature that is easy to be reconstructed by any lab or any other scientist. Freezing point of water and the boiling point of water is what the Celsius scale is. But the Fahrenheit scale was the freezing point of ocean water, and 100 degrees was the average body temperature at the time that Mr. Fahrenheit made it. This makes that ice melts at 32 degrees and that water boils at 212. Not overly convenient, but that is a scale that we use commonly, is the Fahrenheit. But we'll use the Celsius scale. It's a lot easier, a lot better of a scale. It's just not as intuitive because we just don't use it here in the United States. So 0 degrees ice melts, 100 degrees water boils. 1 degree change in the Celsius scale is about just shy of 2 degrees Fahrenheit scale change. Here are the conversion factors. Write these down in case we need to convert them. But Fahrenheit is just 9/5 times Celsius plus 32. Or if you want to know the Celsius given Fahrenheit, it's 5/9 times you take the Fahrenheit minus 32 and then multiply it by 5/9. Now, the lowest possible temperature on any scale is what we call absolute zero, or the absolute temperature. It's the lowest thing. In Kelvin, that is 0 Kelvin. In the Celsius scale, it's negative 273 degrees. Now, the Celsius scale should be, one change in the Celsius scale is the same as a change in degree in Kelvin. Notice that I do not say degrees Kelvin, okay? This is supposed to be 273. I forgot to write the 3 in there. So the Kelvin is Celsius plus 273. We'll never use Fahrenheit except for in weather. You can always use the Kelvin when you're doing absolute temperatures, and you can use Kelvin or Celsius when you're doing differences in temperatures. So let's go into heat. Heat is the random motion of particles in a gas, meaning that they just move around. If you want to click on the simulation, I'll let you guys do that on your own, but it just moves around in the container. The higher the temperature, the faster those little particles are moving, aka they have more kinetic energy. We will take heat to mean the thermal energy of that body, of that object, and is symbolized by the letter Q because H was already taken, both capital and lowercase. So specific heat is the amount of energy a object can take in at a given amount of mass at a very specific temperature change. We symbolize this as C. It's called the specific heat, and it depends on the material. So heat is going to be equal to what I call the MCAT formula: mass times the specific heat times the temperature change. So the bigger the temperature change, the more heat, but they're not equal to each other. You have to include the mass and the specific heat of the substance. Heat is measured in joules, while but we can also use it in a different unit that's commonly used in thermodynamics, and that's the calorie. Now, The calorie is defined as the amount of energy necessary to heat up 1 gram of water 1 degree Celsius. A food calorie, which is different than a regular calorie, is capital C calorie, also known as a kilocalorie, and it's 1,000 little c calories. So 1,000 little c calories is 1 food calorie. So 1 food calorie can heat up a bottle of water, 1,000 grams of water, or a liter of water, 1 degree Celsius. That's a food calorie. Another unit that we won't be dealing with in this class, but you will probably use in later on, is called the BTUs, and that's the British thermal unit. And it's the amount of heat required to change the temperature of 1 pound of water 1 degree Fahrenheit. Again, it's not really convenient. It's kind of confusing, but 1 calorie is 4.186 joules, and a BTU is 252 calories. It's convoluted, I know. Yes, we are changing units from units. Welcome to being an American. Units of specific heat. Now, specific heat is just the calories or the joules over grams per minute per mass per degree Celsius. Now, water is defined as 1 calorie per gram per degree Celsius. So here are some actual units of specific heats. Water is 4,186 joules per kilogram per degree Celsius, or 1 calorie per gram per degree Celsius. Notice that this is a much bigger unit because we're using kilograms here, so this is 1,000 times bigger than these. So ice has a different than water. It absorbs actually less energy. And you can look through all of these. Notice how these are all smaller. Water has the highest that I know of specific heats. So water has a specific heat of 1 calorie per degree per gram per degree Kelvin, and iron has a specific heat of 0.1. If we add the same amount of heat to the equal amount of mass, which one will heat up, have a larger change? And that is going to be the iron, because the iron has a lower amount. If everything else is going to do the amount of heat that the same amount of heat is added, the temperature change has to be going to the iron, because iron can't hold on to that without changing temperature. Now, if we compare the amount of heat energy required to raise the temperature of 1 gram of water and 1 gram of iron, 20 degrees. So we can look at this and actually do that problem. Everything. So iron takes 2,140 calories, while water takes 20,000 calories. Now, heat transfers is a mechanism. It's conduction, convection, and radiation. Now, you know these ones already. You probably learned this probably at the junior high. Conduction is usually done with solids, mostly, and it does when heat is touching without mass transfer, and it's usually touching something. Convection it has to be done in liquids, and it's usually heat that's transferred due to mass transfer, meaning that the liquid is moving from one surface to another, like heat rising, causing the air to rise or the water to rise. Radiation takes place in everywhere, but including a vacuum, and that's just it emits it in the form of light. Now, conduction has this equation here. The heat flow, how much it flows through a surface, has to deal with this equation. It's the thermal conductivity of the substance, so how good of a conductor are they? How big is that area? Is it a big area or a small area? Divide by how thick it is, so the thicker it is, or thinner it is, the more it's going to be able to flow through, and how much of a temperature difference. Is it really cold outside compared to how the temperature difference inside? So these thermal conductivities of common materials. Here's a list of these common materials that are really good conductors and very poor conductors. So we have like silver, very good conductor of heat. But on the other hand, air is a very poor conductor of heat. So we want to use air as our insulator, not silver. But if we want to transfer heat, we want to use silver. Silver, gold, or copper, being really close but not as expensive, is a really good material to transfer heat. So here's an example of that heat transfer from a nail, and it can transfer through that nail. Now, convection is typically very complicated. But it's a very efficient way of transferring. It creates these little vortices where the hot and the cold mix, and it causes these cyclic things going on. If you want to see, there's some really good animations on the PowerPoint. We won't go through them on this slide, but you guys can hit these and you can actually see those animations. We have convections within the Earth's oceans, and actually currents bring up hot water into this region and cool off over here. So that means that the same latitude here and here, Japan is actually warmer than Seattle because the hot water comes up and over here. Same thing here. England is the same height as northern Canada, but yet is cooler in St. Petersburg, which is right here, which is in Russia. But England is warmer because that Gulf Stream heats up the areas of England. We have convection cells within the plate tectonics. You probably remember that from earth science. Now, radiation is this equation. How much power is the heat over time, or this equation? This is called the Stefan-Boltzmann's constant. It's just a number. It's that number. E is the emissivity of the object. It's how well does it radiate. And is based on the material that it is. A is the surface area, and this is your temperature difference raised to the fourth power. So if you can see this, note that the temperature is to the fourth power. So if we double the temperature, the power, the amount of it radiating goes up 16 times. If we triple it, it goes up to 81 times. So a lot more radiation is released when temperature increases. You can see this as a piece of metal glowing at different temperatures. It can get up into 2,400 degrees. It's glowing quite white compared to these lower temperatures. So what is the rate of heat transfer by radiation, which is an unclothed person standing in a dark room whose ambient temperature is 22 degrees. The person has normal skin temperature of 33 degrees, and the surface area is 1.5 square meters. The emissivity of skin is 0.97 in the infrared, where radiation takes place. So what we can do is we can insert all of those things into it. And we can say the emissivity is 5.67 times 10 to the negative 8th, times that by the emissivity of the skin, which is 0.97, times the area of an average human, which is about 1.5 square meters of skin on your body. And then we take the differences between the two temperatures, 22 to 33. They did it in Kelvin here, but we can use 22 minus 33 and put that there. Raise that to the fourth power, and that comes out as you lose negative 99 watts worth of energy, or 99 joules per second of worth of energy. So again, convection, conduction, radiation. Again, if you have any questions, please write them down and ask me in class.